Let's pick up where we left. Last time we prepared this simple setup of protected mode, 16-bit protected mode on 286 processor. It writes directly to video memory through video segments defined for protected mode by a segment descriptor, and then we just hang the computer. Now we need to be able to handle some interrupts. One reason might be that we may want to enable interrupt because now we have them disabled, so we cannot take any input from external sources. But this may be a later goal. For now, the main reason why we may need interrupts is to handle exceptions, because when we start experimenting in protected mode, we would like to see what exceptions happened. In protected mode, interrupt table also consists of descriptors, just like global descriptor table. But of course interrupts use different kinds of descriptor, not segment descriptors like we defined here, but either interrupt gates or task gates, so we need to look them up. No, exceptions are not IRQ. IRQ come from external sources through interrupt controller, programmable interrupt controller, PIC, and exceptions are internal to the CPU. Now, descriptor for interrupt gate or trap gate, they are very similar to each other, contains protected mode var address, selector and offset, and some additional flags. Again, present should just indicate that this descriptor is present. We are going to set 3 lower bits to 1. Oh, the lowest one may be 0. The difference is that interrupt gate clears interrupt flag when entering interrupt handler, so disables interrupts, and trap gate goes to interrupt handler without disabling interrupts, so other interrupts may still happen. Then this should be 110 and present flag should be set. So this should go like this: offset selector, and then A6 perhaps. In the upper byte of this word, this should be descriptor. And let's handle all interrupts. Intel has reserved first 32 interrupt numbers for exceptions. Let's handle all exceptions, I mean. Count numbers from 0. And let's make handlers for each one of them. This should be called selector. In our code segment has selector 1. As said last time, selector can be seen as an offset in global descriptor table, where records are 8 bytes long each. And the lowest 3 bits can be set to some additional values, not important right now. Now we run everything in ring 0. So this is the table, but we also need to define handlers. And inside such handler, let's store the number of exception in a register and jump to some common handler. So that we don't repeat the common code for our 32 exceptions. And here, well, we need some information, so let's set up ourselves to show something on screen. AO is used, so let's use another register temporarily. This is video selector. Perhaps not in top row. Let's set up some offset. Well, screen is 80 times 25. So perhaps let's skip 12 rows and some columns. And let's display at this point. AL is exception number. Let's divide it by 10. Now AH is remainder and AL is result of division. Let's modify them both to ASCII. And display. Character, then attribute. This should be red background and yellow text. And store attribute again. And then just hang. This time hard unconditional hang. Alright, we have the handler. 32 different handlers, in fact. Now let's add another selector. Because, as I mentioned the last time, when we load GDT register, and the same applies to IDT register, its structure is the same as the initial portion of descriptor. So we can just use descriptor and we were also using the same function set base and limit for both descriptors and for GDTR. Therefore we can just set up descriptor for our IDT, which would be a segment that would allow us to modify this table later, and also use it as input for load IDTR. So this is port. We can just load this way. But we have to set up base and limit first. Limit is how many interrupts times size of descriptor. And address of the table. We should note that this is real mode segment offset address. We also should adjust a limit of GDTR because we have additional descriptor then. Later we are going to change it to use some macros so that we do not have to do everything manually, but for now I think this is also a bit educational to see raw numbers. Okay, so we have base and limits set up. Oh, limits should be -1, of course, as always. We are loading IDT table register. IDT table looks like this. And perhaps let's add some invalid instruction to force an exception. It did crash. Something's wrong still. Yes, IDTR label is not really needed there. I could define it like this and set up, but I have set it up in this place because descriptor has the same structure as this register. Descriptor just has more information there. We have 5 descriptors. Oh, here's an error. This should be GDT, not GDTR. This is offset on GDT table. Yes, now it works perfectly. Illegal instruction has caused exception 6, and this is exactly the number we should be seeing. Now let's try something different. Different illegal instruction. Let's try to read from above limit of data segment. No exception. And here we have reached the limitations of DOSBox. Well, DOSBox does not emulate CPU perfectly. As demonstrated here, it does not check segment limits. So to see that kind of error, we need to switch to a more accurate emulator. I have prepared another emulator, but I need first to copy files. Well, this source should be enough because I have copied all the tools earlier there. This time we have an exception. This emulator does all the required checks. This is exception 13, so-called general protection exception. It applies to many protection errors, including trying to read or write after the limit of segment. You can try it another way. We can try to modify limits so that this loop causes an exception. For our data segment, let's use a smaller limit. Let it end at 7th character, for example. And now we see that it started writing the message, reached the limit of segment, and trying to read this character caused an exception 13, general protection exception. So this is the basic protection mechanism, because then program can only access data that it has selectors for, and only in limits. A segment defined by a descriptor may be very small, like here it was just 7 characters. Yes, this also has demonstrated that limit is the address of the last byte that is accessible.